Hello everybody, we are back talking more about dimension of a vector space. All right, let's first remind ourselves what dimension is. So dimension of a vector space is the size or the number of vectors in a basis for that space. So this is something that we've talked about and we have looked at before. We've talked about finding a basis for a vector space and we've talked about that kind of thing, but now we just have a specific name for this. Okay, find our first example, find a basis for the subspace and find its dimension. So these are vectors, A, B, and C are real numbers, and that gives us a real number in each vector. So let's just note this is a subspace of R3. Okay, and we want to find a basis. So intuition tells us that our dimension should be 3 or smaller, and that's actually true, right? If H is a subspace of a vector space V and we are in a finite dimensional world, then the dimension of H is going to be less than or equal to dimension of V. Okay, so you can't go to sort of a subspace, like a potentially smaller space, and somehow get a bigger dimension. Okay, it works sort of how we think it should work. All right, what we're going to do here is we're going to take this vector and break it up kind of like we do when we do parametric vector form. So there's the A's, the B's, and the C's. So we want to break it up into an A piece, a B piece, and a C piece, and see what those vectors are. Okay, those vectors are going to be a spanning set. So the A part, there's 5 here, none here, -2. The B part, there's -3, -1, and 4. The C part, there's 2, -1, and 2. Okay, so these 3 vectors, because anything in our subspace is a linear combination of these 3 vectors are a spanning set. Okay, but the question here is, are they linearly independent, right? Because spanning set is one condition that you need for a basis. Linear independent is another. Okay, so let's think about these vectors and whether or not they're linearly independent. So there's a couple of ways that you could do this. So you could put them in a matrix and row reduce it, okay, and find the pivots. That's going to be a longer way to do it. You can also, but that way always works. So another case is sort of the longer, more tedious way sometimes is the surefire thing. But let's just look at these 3 vectors and see if we see any relationships here. And I do see, right, okay, 5 and -3, that gives us 2. 0 plus -1, that gives us -1. -2 and 4 gives us 2. So if we call this, let's call this U1, U2, and U3, we see this relationship of U1 plus U2 is equal to U3. So that tells us that these 3 vectors are not linearly independent, they're linearly dependent. And then we're going to use the spanning set theorem. Tells us we can throw out the redundant one. So let's throw out U3. We still span. And now we want to check, is just U1, U2 independent or dependent. And if we look, right, when you just have 2 vectors, you can examine, is one a scalar multiple of the other one? To get from -1 to 0, you'd have to scale by 0, but the other 2 aren't scaled by 0. So yes, they are linearly independent. So this set of 2 is a basis, And so what is the dimension of this subspace? Dimension of this subspace is size of a basis. So the dimension is 2. All right. Great. And another way, if you have a hard time sort of just seeing the relationships between the vectors, just put those 3 vectors in a matrix, row reduce, and find the number of pivots. Okay. All right. Now let's look at null space and column space. All right. So null space and column space, my favorite subspaces. And we want to find the dimensions of each of these. And here's our matrix A. All right. First thing to notice is that A is in echelon form, which is really nice for us because we can see where the pivots are. All right. So let's remind ourselves what column space and null space are. Null space is all solutions to the homogeneous equation AX equals 0. Column space is the span of the columns of A. Okay, and let's remember from the last section, we found a basis for the null space by row reducing and solving this homogeneous equation. And every time you got a free variable, that corresponded to a vector in your basis. Okay, so that is going to happen in general. Dimension of the null space in general is going to equal the number of free variables or the non-pivot columns. Okay, and then with column space, right, all of the columns are a spanning set, but we only want the ones that are linearly independent because a basis has to be independent. So we only want the pivot columns. So dimension of the column space of A is going to be the number of pivots. Okay, and that's going to be true in general. That's all we have to do. So let's circle our pivots here. So -3 is a pivot, 7 is a pivot, and 2 is a pivot. So for us, okay, dimension of the column space, 1, 2, 3 pivots. Dimension of the null space, that's the number of free variables, where we have one column here that corresponds to a free variable and another here, so that's 2. So there's our dimension of column space and null space. And if we notice, right, that's all of the columns. Every column either has a pivot and goes towards null space, or it does not have a pivot. Every column has a pivot and goes towards column space, or it does not have a pivot and go towards null space. So we end up with this correspondence all the time that dimension of column space and dimension of null space, well, that's going to be just all of the columns put together. And we'll talk more about that in the next section. All right, thank you.